Great, wonderful introduction. Okay, thanks y'all for coming. This is great. I last came to Chico when I played rugby for UC Santa Cruz, so it's been 25 years, and I don't really remember much from that experience. You know what rugby parties in Chico are all about. But anyway, that was 25 years ago, and I've been a lot of places since then, so it's really a pleasure to be back here and tell you about what I've been up to basically over the last decade or so, including my PhD research in Nevada, and then the work I've been doing in Alaska for the last 5 years or so. So the title of my talk today is Far-Field Plate Boundary Deformation, Paleoseismic Perspectives from Nevada and Alaska. But first, a word from our sponsors. A lot of this work was funded at UNR through Desert Research Institute, Geologic Society of America, National Science Foundation, while I was working at the Center for Neotectonic Studies. And then in Alaska, the Alaska Gasline Development Corporation, while I was working at the State Survey, sponsored a lot of this work. And then I'm not sure if these guys sponsored me or I sponsored them, but now that I'm giving a talk in Chico, maybe it'll be more amenable to it in the future. So I'd like to give a shout out to my Alaska field team. A lot of my Nevada work was done by myself, but we have a former alum, Elise Bagler here, Chico alum, and we have Dick Rieger, who was born and raised in Chico and spent the last 40 years doing glacial research in Alaska. Great guy. And my son Timmy here, just some fun stuff. So I'm going to talk a little bit about Nevada. I'm going to give you an outline in a second, but this is a picture of the fault scarp runs right across here in Spring Bloom. This is the 1954 Fairview Peak earthquake scarp. It was about a 7.5 big earthquake, caused about a 4-meter scarp here. And it's just it's a beautiful time of year to be out there, and you can drive right up to the scarp. It's a good place to start. There's actually a sign on Highway 50 that says earthquake fault scarps if you get lost. So a little bit of outline. I'm going to just introduce paleoseismology, tell you a little bit about what I do, some of the terminology, show some typical landforms that we find along the different types of active faults. And then I'm just going to take paleoseismic studies in Nevada and Alaska, first Nevada and then Alaska, studies on individual faults, and then put them in sort of a regional context to see if we can't use fault studies to sort of break down the plate boundary deformation amounts. So first of all, what is paleoseismology? Paleoseismology is basically just the what, where, how big, how often earthquakes happen, the distribution of individual earthquakes throughout the landscape, rupture patterns. We like to figure out sort of when the last earthquake happened, when the last several earthquakes happened, and how fast individual faults are moving. We know this pretty well with geodesy these days, but we want to try to figure it out in the geologic record to see if we can match that. So what are the tools? How we get about this? A lot of field mapping, of course, and then it's really multidisciplinary. So geomorphology, stratigraphy, geodesy, remote sensing, geochronology, and I'll touch on a little bit of all these subjects as I go through these slides. So here's a big trench in the rain, Cathedral Rapids Fault. This is Rebecca Ellen Farrell measuring some section of me drawing maps of the stratigraphy. Here's kind of what the stratigraphy might look like in a big trench. Just some fun stuff. So the different types of faults have really distinct rupture morphologies. This is for normal faults here. This is the Bora Peak ruptured in 1983. Typically about tens of meters wide is the width of the deformation. It'll generate a scarp. Sometimes there'll be a little graben on the hanging wall of the fault. Here's the Shell Creek Range. There's a nice oversteepened basal scarp, and you get a lot of these typical triangular facets along there. This is what you kind of see in the subsurface. You get an offset of a surface, and then you erode that surface and make this little wedge, call that a colluvial wedge. And then after several earthquakes, we can kind of go in with a trench and look at the different ages of colluvial wedges to determine when earthquakes happen. So in compressional environments, reverse and thrust faults, you also get you get folding of the hanging wall as it thrusts up over the footwall. You can see this on Mad River Fault Zone in California. You can see this folding right here above the fault. This is illustrated in a couple schematic diagrams. You also generate colluvial wedges as the scarp erodes after the earthquake, but they're a little bit different, and you can see the folding and stuff, and so you see that they're different also from the normal faults. And then also, sometimes there's subsidiary strands, but the zone of deformation can be hundreds of meters wide on the hang wall, in the folding area, but where the main surface structure is generally pretty narrow. And then finally, at the end of the spectrum, you have strike-slip faults, where the zone of deformation can be 50 to 100 kilometers. This is the southern San Andreas Fault, so there's several faults, but there's just a big damage zone on the surface of the Earth. There's also this diagram up here showing the general morphology of things. There's offset streams, shutter ridges, little uphill facing valleys, and there's a subsidiary strand, about 100 meters from the main strand. So that's pretty typical. Here's the Denali Fault in Alaska. You have two strands of the fault here and a sag pond in the middle, a little depression. In the subsurface on strike-slip faults, you often have stratigraphy that doesn't match across faults, and also, again, you have this wide zone of deformation. And then so we look for fault tips that come up, and so there was an earthquake, generated this fault here, fault E4, and then more fluvial deposits buried it, and then those were subsequently offset. So we go through the stratigraphy to look for this sort of stuff. So I just want to start with the Nevada part of the story. Here's Chico for reference, big red star in the western United States. Deformation in the western United States generally dominated by translation of the Pacific Plate along the San Andreas Fault. Here in yellow, the 1906 earthquake. There's a number of faults. Slip is distributed through the Hayward and Calaveras faults in the San Francisco Bay Area. And there's then along the backside of the Sierras is the Walker Lane, which is moving at a little less than 10 millimeters per year. It's also taking up some of that northwest directed translation. And then you have the Great Basin, which includes the intermontane drained area of central Nevada. Generally, the basin range between the Wasatch Front and the Sierras, but the Great Basin is sort of the interior drained portion of it. So I'm going to talk about the field area here in a second in this box. But basically I'm concerned about, can we match the geodetic rate, which was first talked about at Bennett in 2003, where they had about 2.8 millimeters per year across the central and eastern Great Basin. So can we see that in the geologic record? Was a question that I was hoping to answer. So here's the geodetic crustal velocities. This is 10 millimeters per year for a scale. So you can see they're very small in the central part of Nevada, but they increase as you get over towards the Sierra Nevadas. So the old thought was that it was a rigid crustal block and the whole thing was translating to the west. So here's this box, this red box, shows that nearly every mountain range is bound by an active fault. There's faults in white, there's faults in red. The red ones are the ones that I worked on. And we tried to do a transect across to see if we could estimate the geologic slip rate by looking at every single fault. So a couple things to note in the geomorphology: if you have fast uplift rates, you get steep fans that form right at the range front, kind of like what we have over here at the Toyabe range. If you have slower rates of uplift, the fans are able to cut through the older fans and deposit farther out in the valley, like this lighter colored fan here on the Antelope Range. And they're generally a shallower gradient. So we kind of use those as proxies for fast or slow uplift when we're first looking at these places. So the method I use to figure out how much strain or how much deformation we can quantify across Nevada is to first map the location and the amount of late Pleistocene displacement along faults, map the superficial geology and the quaternary stratigraphy, identify the number of events by digging trenches and also looking at scarps, and trying to get estimates of the age of the scarps, age of the faulted deposits, and then just dividing the distance, how much offset by the age of the deposits, to get a rate to sum it across the region. Here's some of the typical deposits we find out in the Basin Range. This is a cartoon that shows shorelines, little bars from when the lakes were up this high. They dry up and leave playas behind. Young fans come out of the mountains and cut through older fans. And then you have these triangular morphology, range front morphology. You have some older fans that are more dissected. This is really typical of the entire Basin Range and sort of the types of things we look for to get relative age constraints between the different deposits. So I'm just going to go through a bunch of examples. I'm not going to show every map. Well, I kind of will, but anyway, we'll see. Anyway, this just shows a picture of a scarp right down here at the mouth of Wiley Creek, and a little cartoon of that picture And so it just shows that you can use the stratigraphic relations of inset relations. There's a surface here, there's another surface that's a little bit lower, and then at the base of the scarp in the right light, there's a oversteepened base right along here. So that just suggests three earthquakes. The most recent being this oversteepened basal part that's about 1 meter, and then one to isolate this surface and one to isolate that surface. Here's just an air photo that shows some of the stratigraphic relations I've shown on the cartoon. Here's a well-dissected older fan.
Are keys in here?
Keys?
On those chairs?
No,
Don't see them.
we'll let you know afterwards.
Has anybody seen the key? Okay, older surface, well dissected. Here's an intermediate age surface. It's dissected, but not as much as the older one. And so this surface is offset by about 30 meters along the basal scarp here, along the fault. There's offsets on the intermediate surface of just several meters, and then the younger surfaces are not offset. So the stratigraphic relations between the different fan units help us determine the relative age of the fault event. So Simpson Park Range, one of my favorites, is really awesome. Fault right along the base of the hills here. It's lined with springs, so water's coming out along there. It's a nice oversteepened basal facet there. And then here's a field truck for scales, about a 2 meter scarp on the fan here. So again, we use the stratigraphic relations to understand the age of the faulting. So on the lower left map, there's a fault cutting across a QFI intermediate age fan. And then we also see it's cutting across shorelines. The shorelines were when the lakes desiccated about 13,000 years ago. So that gives us an idea, here's a photo of it, an idea of when this earthquake happened because it cuts these shorelines. So that earthquake happened after the lake drained out. So then, just to give you an idea, to do this, I had to do a lot of mapping all over Nevada to find, on every fault there might be 2 or 3 sites that warrant detailed investigation. So you have to find them first. That was the tough part. So a total of 300 kilometers of quaternary strip maps were created to find the sites on each one. So paleoseismic trenching is probably the most effective way to observe this stratigraphy in the subsurface. And so here's just a photo of the surface act of trenching, which is always pretty exciting. And just some examples of some of the trenches we dug. These are big trenches. These are 50 meters long. They're 8 meters deep. Some of them they're benched for safety. See the benches here. So we kind of sit over on the benches and we'll try to keep one wall vertical. And I already kind of discussed the colluvium that comes out of the scarps once an earthquake happens. So then here's some examples of the relations exposed in trenches. These are sort of 3 typical things that you see. Here's a graben with the 3 different colors here, 3 different ages of graben fills. So that's how we get 3 events in that trench for an offset of about 4 meters. This one in the middle is kind of more typical of the cartoons I was showing, where you generate a scarp and you fill it with colluvium, generate more of a scarp, fill it with colluvium, and do it again a couple times for 3 events. Each color is a different event. And then this is just a single event scarp. It's only 1.6 meters of offset, but it has a nice fissure and a little colluvium. And here's just some more of the same. So some pretty typical relations that we see. In this one, the lake came up. There was an earthquake, colluvium was in gray. The lake came up, buried it, and then the lake deposits were offset. And then the dark gray is another colluvium. So we just see these things, and they vary, but the theme is pretty similar with normal faults. So one way we can date the scarps, the age of the scarp, is with the diffusion equation. I'm not going to get into the math of that today, but I just want to point out that it works if it's a single event scarp, because if you have a second event, it's going to change. Diffusion just means you make it kind of a vertical scarp, and it's going to diffuse through time at a certain rate. So this is an example of a 9,000-year-old scarp, and then a 55,000-year-old scarp, pretty degraded one. So I tried that in a lot of different areas. Soil pits are used to correlate map units in the map area, and it's also used to get an estimate of the relative age of the deposits. So this me in the bottom of the soil pit in the Taiwan range, and this white powder is carbonate. So the amount of carbonate in the soil profile has been correlated with other dated surfaces around the west, so you can get an idea of how old a surface is by how much carbonate is in the soil. So in general sense, that's what I did on all of these fans that were offset. So here's some examples of those soils. There's the white carbonate, and we kind of quantified that by just relative percent of the soil. Here's the descriptions, and it just shows the base of the soils. The soil's about the same thickness on all of these surfaces going across the Central Basin Range. I'm not going to get into the details of it, but oxygen isotope stage 4 from the marine record is about, from benthic forearms in the ocean, is about 50 to 70,000 years. And so we think these fans are about in that age group based on the relative carbonate in there. So that gives us a proxy. So I looked for the intermediate age fans that were offset as my time limit to calculate my slip rates. So this is a pretty confusing picture. I don't want to get into details just to show that the Sierra Nevadas are on this side, and the Wasatch is on this side. Here's the fault map. Each one of these lines is a fault, and each one of the circles is an earthquake on that fault. So what to take away from it is the frequency of earthquakes is much greater on the margins of the Great Basin, but the red fault, the red zone is where I worked, and there are earthquakes on all of these faults. They're all capable of generating damaging earthquakes. Here's all the red faults in here in my field area there. So it just kind of shows you the distribution of earthquakes across the Great Basin. So what I did, you're not going to be able to read this, but I just added up all the vertical offsets, made some assumptions on the dip of the fault, and then estimated 48 meters of extension across the whole region. And with some geometry to sort of resolve all the faults. They're all slightly different strike to resolve them all to a north-south strike, so you're kind of comparing apples to apples. I get about 0.8 millimeters per year of extension. And considering some of the uncertainties in the dip of the fault and stuff, it can range from 45 to 70 degrees or so. These numbers are from a 60-degree dipping normal fault. We get about an average of about 0.8 millimeters per year of extension across that region. And so when you look at 0.8, right in there where I work, and there's 2 millimeters per year of extension in the Wasatch that's been documented in other studies. So that gets us back to, we have the first order relatively good fit to the geodesy from that 2003 Bennett study. So in the greater scheme of things, how does it fit into the plate boundary? So if you start summing up the individual rates across the Pacific North American plate boundary, you start with about 25 millimeters per year along the San Andreas Fault. Hayward Fault, 7 to 9. These are just measurements from other studies, geologic studies and geodesy. Calaveras, 4 to 6. The western foothills, there's some faults around. We got the Inks Creek Fold Belt here in Chico, but there's some faults in the western foothills. The rates are pretty poorly constrained, but you could put a millimeter or two in there. The Walker Lane, 6 to 9 millimeters per year. And then you start looking at central Nevada, where I work, about a millimeter, and then the Wasatch is 2. And so when you look at that, you get, with uncertainties to first order, you can match the geologic rate. Geologically, you can match the rate that's been measured geodetically with satellite geodesy. So that's a pretty cool result, and what it just tells you is that if you pay careful attention and you get all the main faults across the region, you can get a really good handle on that rate from a geologic perspective. So then I'm going to sort of do the same thing for Alaska. I'm going to show you sort of some results of paleoseismic studies in Alaska, some cool photos, and just get into the Alaska side of the story. I'm going to start with the regional seismotectonic setting, and then I'll go through some of the individual fault studies, and then put it into the regional perspective, similar to what I did in Nevada. So here's Alaska, and the black dots are earthquakes. So you can see there's a lot of earthquakes concentrated along the Denali Fault here and along the subduction zone. This is a Quaternary Fault Map of Alaska that I published in 2012, and the different colors are the different ages of earthquake or of fault activity. Where red is that it's had a historic earthquake, and orange is Holocene. What you get from this is that there's a whole lot of territory with no faults, and that's just because these are the only ones that have documented late Pleistocene deformation. So that was the rule for the U.S. Geological Survey National Quaternary Fault Map, is they have to have documented evidence of quaternary deformation. So that's what we get for Alaska. We know there's more. There just hasn't been a whole lot of study. Access is very difficult, and there's a lot of more discovery to be made. Here's the bedrock fault map. So go back and forth from there to there, there's a whole lot more faults out there. Whether they're active or not, we don't know. But there is potential there. Okay. So deformation in Alaska is driven by subduction of the Pacific Plate beneath North America at about a similar rate to the Pacific North American plate boundary in the western U.S. So about 50 millimeters per year. And then there's a microplate here called the Yakutat microplate outlined in brown. It's an oceanic plateau that is colliding into southern Alaska and causing a tremendous amount of uplift in the Wrangels and the Chugach St. Elias range, where you have Pliocene deposits that are up at 14,000 feet. So they're rocketing, and they're oceanic sediments, so they're rocketing out of the ocean at rapid rate. Here's the geodesy picture in Alaska. I don't want to dwell on that too much, but this scale down here is 30 millimeters per year. So what's just showing you that the length of that line and the length of these is you have tens of millimeters per year being accommodated in the Chugach St. Elias range and in south central Alaska, which doesn't leave a whole lot for northern and interior northern Alaska. And you can see these arrows are really short, but the station, the distribution of stations is pretty poor, and so the resolution of that is pretty good, or not well constrained. So here's some of the field areas that I'll talk about, outlined in red here. I'll have just a few examples in each area, just documenting the paleoseismic behavior faults, and so I'm going to start with the Castle Mountain Fault. Castle Mountain Fault sits in south central Alaska. It's basically the backstop of the Four-Arc Basin. That's been accumulating sediment. Here's the subduction zone cartoon. Four-Arc Basin is here, and the Castle Mountain Fault extends along the back edge of it. It's been accumulating sediment since the Cretaceous up to the present. The basin itself is being deformed by sort of westward motion of the Kenai Peninsula, which is here. This is Anchorage, by the way, for reference. Cook Inlet. So these purple lines are folds in the base of the Four-Arc Basin. So I'm going to be showing some examples of the Castle Mountain Fault, which is right here. And Hausler in 2000 published this industry seismic line that documents a 4-kilometer wide anticline in Pliocene sediments on the north side of the fault. So the big debate for a long time was whether this is a strike-slip fault or some kind of reverse fault. And so that was one of the questions that we decided to attack, try to learn more about the deformation style there. So we had lidar flown. Lidar is high resolution topographic data. And so this is just a DEM colored by elevation. But even just in the raw data, you can see color contrast right along here. That's the Castle Mountain Fault, and it steps over here. And faults in here too. So you can see that. And here's the scarp. So there's a person, geologist, Rachel Foman. And so the scarp's a little bit taller than her. And then the picture here on the right is just a fantastic photo. The fault shows up really beautifully, even without the line. The northern uplifted part of the fault is better drained, and so the deciduous trees can grow on it. And so whereas on the south side of the fault, it's more black spruce and marsh. So there it is. We also did, similar to Nevada, the Quaternary Superficial Geologic Map of the Castle Mountain Fault. And what's shown in olive and in pink are outwash deposits when the glaciers were pulling back, which is massive outbursts of sand and gravel. And then this blue is the Elmendorf end moraine, the late Elmendorf Stave glacial advance, which was about 14,000, 15,000 years ago when it pulled back. And then the whole region uplifted out of the sort of intertidal area and is now basically abandoned except for the Little Mississippi River, which cuts through this beige color. The images down below come from this area right up here, and this is a slope map and a lidar map. And the interesting take home here is that these stream channels no longer have water. They're grassy meadows. They're abandoned early Holocene stream channels from when it was right at sea level almost, and it's since rebounded. And the interesting thing about it is that these stream channels cut across the fault. Here's the fault trending east-west across the image. Shows up really nicely on these left stepping and echelon scarps on the slope map as well. What to notice is this is a sand dune that goes across it. It's in the forest now, so this was a sand dune in the early Holocene, and it's not laterally offset. So it basically goes straight across the fault. And these stream channel margins are not laterally offset. They basically go straight across the fault. So from that, we can infer that there hasn't been very little lateral displacement in the Holocene. This profile is going down one of the stream channels, and so there's several scarps, and there's a cartoon of what it's in there. So the results, we get about half a meter to 5 meters in height is the scarp over the Holocene, and it gives us a slip rate of about half a millimeter per year. And so we conclude that it's best characterized as an oblique high angle reverse fault, which is consistent with the geophysics. So we trenched this fault, and again, here's the margin of a ground moraine, and then the fault's cutting across here, and we don't see any lateral offset of that margin. So we excavated a trench right here. This is the scarp coming across right there. And this is what the stratigraphy looks like, just a lot of fluvial sands and gravels. And even just in the uninterpreted version, you can see sort of some folding in the gravels. And I'll show you the log there.
Rick, we use the colored tags.
Sorry?
What are the colored tags for in the trench?
These colored tags in the trench wall are what we use as paleoseismologists to, and it's not dissimilar to what archaeologists do as well, to mark the base of contacts. So this sort of orange sandy unit here is marked by blue and white flags going along here. And then we also mark faults with red flags. So there's a fault right there. And if you look closely, you can see this dark color at the base central part of the photo has a really abrupt contact there and there. And so those red flags are marking faults where that sand bed is offset. And this one comes all the way up to there. So anyway, that's a nice fault plane right there. So to answer your question, we just use it to mark stratigraphy and keep track, and then we get graph paper out. Nowadays trench logging is getting gotten a little simpler, where we can just take 50 or 60 photos and then put it into a program called Arcgis, and it'll spit out a point cloud of a 3D model of the trench wall. And so what we'll do is we'll print that out and we'll take that to the field and draw directly on that. So that's kind of the new way. But the old way is just to set up a grid. There's a little grid of orange lines going across at meter intervals, and you just take graph paper and you measure to each flag, plot the flags, and get your log. And so that's what a log looks like. So this is that offset I was talking about down here on that sand unit right there. And so what the bottom line is, we have sort of some folding, typical stratigraphy for high angle reverse fault. We also have some thickness changes and some upward fault terminations, which are really similar to Strikeslip morphology. So we think we have a little bit of both happening. But the lateral component is small. So what we can get from this is we have an upward fault termination here. There was an earthquake, then it got buried by the yellow sand, and we have some dates in there, about 12,000 years. So we have an earthquake that happened prior to 12,000 years ago, and then sometime in the Holocene we had one that broke the surface and created the modern scarp. So we get a long, greater than 5,000 year recurrence. So it's not having earthquakes very often, but they're big enough to cause 1.5 meter scarps, which means magnitude 7 or so. Not going to spend a bunch of time on the Past Creek Fault, but it's a cool fault. This is the Alaska range right up here, and this is the Denali Fault in orange and red. I'll talk about that next. But here's the Past Creek Fault. Relatively small fault. How it may connect to some of these black faults that have never been really studied in detail is up for debate. But one cool thing about the Past Creek Fault is that modern microseismicity all shows thrust fault mechanisms. It was originally mapped as a normal fault in bedrock mapping back in the 60s. But we are sort of hypothesizing that there may be a fold and thrust belt on the south side of the Alaska range. There's a lot of topographic relief along here. And there's a lot of structural grain like this, and the Denali Fault is bending around, so it might be causing some compression in this region. So this is all work that's just really started and haven't spent a whole lot of time out here. But here's an air photo, infrared air photo, and the fault runs right along the white arrows. So you can see that there's some ponds. These ponds right here are these ponds. So there's a scarp going along here that is ponding water in the creeks and offsetting glacial landforms. Here's a scarp up here with geologists standing on top of it, so it's a good 3-meter scarp. So it's a pretty good sized scarp, and it's definitely an active fault. And how, I guess what I can say in the regional strain budget, the story of this talk is that it's entirely possible that you could have several millimeters per year being accommodated along the southern side of the Alaska Range. So this is my favorite, Denali Fault. The Denali Fault had a 300 kilometer surface rupture in 2002. A couple pictures of it. The bottom picture is up near the Nenana Glacier. The fault goes right through here. It's just in bedrock. It's causing this little, just a little trough in bedrock. And this was just completely scoured, even 11,000 years ago when the ice pulled away. So this is the last couple of earthquakes being reflected in the bedrock. And then up here, the fault is running, our survey here is set up on the fault. So this is I'll show you some better pictures of this in a second, but it's just going right across here. So this little mound of material is being pushed up along the fault. And there's our helicopter coming in. So it's pretty fantastic. I showed a picture of this earlier. This is looking the other direction, but here's a sag pond. This is, 500 feet or so up from the valley bottom, so you have this sort of side hill bench, several traces, about 15 meters across, this little trough valley filled with water. That's called a sag pond. And here's another uphill facing valley, a little bit of snow in it, along right in Denali National Park from the window on the bottom of the helicopter. You also get these sort of fissures on these steep, cobbly alluvial fans, and some of them are greater than waist deep. But we think that those fissures were created in the last earthquake, which on this trace of the fault is probably a couple hundred years ago. So this is where we are. Sorry, I should have had a regional map in here too. But anyway, this is the Alaska Range, which cuts across the whole central part of Alaska. It's a major range with Mount McKinley or Denali and Denali National Park. So the red shows the 2002 earthquake rupture, which started here in the west and propagated to the east onto the Tshunda Fault, 300 kilometer long rupture. It started a week earlier with a 6.7 precursor near Nenana, right near that bedrock scarp that I showed in the last slide. And then a week later, it ruptured in the 7.9 that propagated down the range. So this is INSAR data. This is not quite as good a resolution as lidar, but it's still pretty good. It's like 3 meters or something. Anyway, so this box here is a blow up of the INSAR data. We use that to help map the fault trace through here. And I know that's kind of hard to see, but there's a lot of little left stepping strands and real typical Strikeslip morphology. So the stars just show other people who have worked along this stretch of the fault. We're really curious about this side of the fault because this side broke in 2002. I think the last earthquake along here was a couple hundred years ago. So given the slip rates, which I'm going to talk about in a second, it's about 2 meters worth of strain is accumulated on that part of the fault, ready to go in the next quarter. And each earthquake has anywhere from 3 to 5 meters of offset during the earthquake. So we're about halfway there, or maybe a little more than halfway there for an earthquake on that side of the fault. And that's of concern to Denali National Park, the highway, the railroad, all major infrastructure corridors in Alaska, and also natural gas pipelines that are coming through, being planned to come through that area. So here's that fan where the survey gear was set up right up here, and there's a couple traces mapped in red, kind of light to see here. So this is an alluvial fan. That was the focus of our investigation here. So this is looking north. This photo here is from the helicopter, but kind of looking south. And the interesting thing here is you see this stream comes down, and it's offset to the right. So we know that Denali Fault's a right lateral fault. How fast is it moving? We're trying to figure that out. Here's a trench we dug. Unfortunately, we couldn't get any information as far as datable material out of there, but the colluviums and the upward fault terminations in this little hand-dug exposure indicates 3 events for sure that we can pin. So say, for example, this fault comes up and is terminated at the base of the blue, and the blue is a colluvial wedge. And fissures with peat mass being dragged down, that's the most recent event. And the brown is an intermediate event. And then there's this jumbled mess down the bottom that probably represents 4 or 10 earthquakes or something, but we can't resolve anything down there. It's been through the mean. So what we did, I'll just go back to this guy. We took this as a differential GPS instrument, and we put a backpack on and hiked all around that fan and took points, X, Y, Z, latitude, longitude, and elevation. And by doing that, we generate a DEM. We generate a point cloud, it's called, of that information, X, Y, and Z data. And so this is a fan, the area that we walked, and these are the channels you can see, and the big one that's offset that I had a photo of a minute ago. And from this, we can do profiles in ArcGIS. We can also generate contour maps and slope maps. So the channels, this is a curvature map actually, so the channels, the convex up channels show up really well. And then this is the shutter ridge. So we did this so we could kind of figure out, we could slice this up with scissors or in Photoshop, if you're good with that, and back slip it. Take the slip from the earthquakes that have already happened and restore them. And when we restore them to 8 meters, which is here, this channel lines up with itself. And so these two profiles here, the black one is profile number 2, and the red one is profile number 1. And so when you back slip it 8 meters, those two channels line up for the middle diagram here of the profiles. And so you can do that and line up various channels as you go. And then if you go all the way to 43 meters, there's a nice channel that lines up as well. And so we've done that. There's 8, 25, and 43 meters. And I know this is super tiny to see, but once you do the 43 meters and you line up this channel, the margin of the fan lines up with the mountainside. And so you basically restore the whole fan morphology. So if I back up to, just the picture of the fan, it's really a pretty incredible sight. You can see how the margin of the fan is right about here. You can see the vegetation really likes the fan material, and it's kind of a light yellow color as opposed to just the bedrock, which supports the trees. So you bring that up to the fault, and then to get to where the fan's coming out of here, you got to offset it, and that's the 43 meters that we restored. And we know that material's not coming down here anymore because it's in size about 10 meters at the head right up here, and all the creep goes on this side now. So it's basically abandoned. So we wanted to figure out the offset, and then we wanted to figure out how old it was. Well, each of these black dots is a place where we sampled for beryllium-10 surface exposure dating. And so this is the surface exposure dating kit up here. You basically take a hammer, take a chunk of a rock, process it in the lab. I did that with Dylan Rood out of Scotland. And so here's a probability density function of the ages of the boulders. Here's the data. You can't read that, but basically this peak is about 6,000 years. So we think that's basically close